growth, which stands for Global Relay of Observatories Watching Transit Happen. So it's mainly like a group of telescopes that come together to take continuous observation of all of these uh, sources that we call as transients, which are like this lasts for a very small time on astronomical scale, roughly lasting for about a week or so. So this particular paper is about like discovering a very rare class of this sources called TDEs, which are this disruption of a star when they come close to very supermassive black hole and all. So I would like to start with a very basic idea, which is I'm not really sure if you are able to see a lot of things on the screen. Yeah. The first one is a very deep image taken by Hubble, and you can see that like there are a lot of stars as well as galaxies in the field. As far as my research interest lies, most of these like stars and galaxies are boring for me because they don't really evolve on time scale of weeks or days. Where my interest lies, basically we look for these candidates called transients, where there is something astrophysical process happen and they brighten up by a few several order of magnitude. So on the left you can see there is nothing in this image, and on the right hand side there is some source that will pop up at this location. These are called transients. There are various classes of it, ranging over several, belonging to several astrophysical processes. Novae are usually like mass transfer between two stars. Supernovae are likely associated to the death of the massive star. Similarly, gamma ray bursts are essentially the birth of a black hole and the launches that which lie in the gamma rays and all. Also, there are these new type of transient called F-ports, which are very blue and very fast, and all of these are like very bright category of the transients. So I'm using this plot to like figure out why this discovery is important, how it is unique, and how it differs from all of these different classes of the transients. Starting with the thing, we use this particular telescope named Dorothy telescope. You are hardly able to see it. So this is the dome in the night sky situated at Hanle, Ladakh. And the telescope inside it is this 0.7 meter telescope named Growth India. And this is accompanied by a camera which is about 16 megapixel sensor. You can assume like your phone camera is bigger than that, but it's much more advanced in terms of quantum efficiency, roughly ranging more than 90% or so. Also, it gives a field of view about 0.7 by 0.7 degree, which is roughly twice the size of full moon in the sky. And the sensitivity of this telescope is much more deeper as compared to. So this is a unit in which we measure the brightness of these stars called magnitudes. This is the log scale brightness. So this particular telescope can see about 1,000,000 times fainter object than what humans can see in the night sky. And this is the telescope in our collaboration with the other telescope we have used for the discovery of this particular thing. So on 11th of the Feb at roughly 10:35 or 36 UTC, we detected a candidate in the one of the partner telescope images, where you can see that this is the raw image and this is the reference image from previous epoch. And when you take the difference of this, there is a very nice candidate popping up. This is one of the previous survey telescope that has taken an image of the same epoch, and we found that there was nothing over there. So this is essentially a new candidate. This candidate started there was no observation of this telescope before this, as confirmed by this reference image as this construct image, and it started evolving very rapidly when it brightened up by a couple of magnitude over the course of just one day or so. And after that, it soon started to decay. So this is like very rapid evolution when it brightened out and started decaying. At this point of time, we have set up a few automated boards which alerts us, okay, there is something which is evolving very rapidly, and those are very important to find these transients in the real time. So at this point, we got an alert, and then there is a nice campaign starting to which started following this particular event in different energy bands, and we found that it started decaying and decaying very rapidly over the course of a few days. But what happens after that is that the decay process started dying out, and it almost started flattening out. Over the course of a few days, and up to 30 days after the discovery, it almost became flat or so. If you look at this plot in a bit more detail, let's get rid of all of these unnecessary bands. Let's focus on just one band, which is R band, roughly lying around say 700 nanometer or so. And let's change the scale that was there on the anti-log scale, which gives this flux instead of the magnitude. Now you can see that there is very rapid rise in this particular candidate, and then it started decaying very rapidly. and then there is the flattening part. And in between these two things, there is this part where there is a slow transition happening, right from this first very rapidly evolution stage to the very like shallower decay phase. And that's where like our telescope did the best job, because all of the star markers you are able to see are the observation from the GIT, where we found that like this this zoom in part actually started from covering from the decay phase only, where we found that the earlier meteor was actually decaying with a power low, and as soon as up to 3 or 4 days it continued that, and after that the decay started slowing down. So in this particular part, it actually has like all the information contained from the very early phase as well as from the later stage when it is transforming into the second part. Apart from this evolution that we have seen, very rapid evolution, we also have a few things which are okay. Okay, so this will also work. So on the left-hand side, what we have plotted over here is the brightness of that particular candidate, how it has evolved, and on the x-axis, what we have is how rapidly it has evolved. So this is how many for how many days it has actually remained above the peak of this, so above half of the brightness of this particular candidate. So this is the candidate that I am talking about, 82022 CMC, and over here we have compared it along with the like other classes of the transients, including the supernovae, luminous F-board, and as well as the afterglow, all the candidate classes of the transient that I have showed on the second or third slide. So looking into all of these things, that we will compare all of these one by one, we see that the brightness is much more than all of these supernovae that we are seeing over here, including the corpus supernovae, supernovae of class 1A, as well as the very super luminous supernovae. None of these are able to explain the brightness that it has shown. So the factor of about a factor of 2 in the magnitude is something which we are missing in all of the supernovae to explain this particular emission. If we compare this with the GRB afterglow, it actually summarizes everything well, but it did not evolve like a GRB afterglow. It started decaying very fast and then slowly transitioned into a very slow decay phase, which is not we have seen for the GRB afterglow. Possibly optical transients also are somewhere like very low in terms of dynamics. So you can see that at least an order of magnitude is more energy required to explain this particular candidate instead of this F-board. So what happens is that like okay, I think everything is missing from the slide. I'm not sure why. So what is happening over here? The model that can explain this particular thing is I will explain from over here. Yeah, so if you see, like there are these two parts. One is like very rapid evolution in terms of rise and decay, and then it is going like shallower into this particular part. So the model that can explain this thing is like you have a very supermassive black hole at the center of a galaxy, which is say 10 to the power 8 solar mass or so, as per estimation by our data, and you have a roughly a solar mass of star which is going very close by to this particular object sitting at the center of the galaxy, and as it is getting close by, it is being ideally disturbed by this particular thing, and the mass of this star which is passing close by started accreting around this black hole and form an accretion disk. So the model is something like you have a black hole and there is an accretion disk around it, which is giving emission in terms of tidal disruption event, and these events, this black hole when it has an accretion disk around it, we have seen previously that they sometimes launch in jet which lie roughly in the gamma ray, somewhat similar to gamma ray bursts, and this jet launching part gives rise to another component of the emission, which is this very rapidly decaying and rising component that is coming out of it. So there are essentially two components. One is very rapid rise and decay due to the jet component of this particular thing, and the second component which is coming, which has very shallow decay, is coming from the tidal disruption part of this particular candidate. So together both of these can explain what we have seen, and that's what the model we have proposed in this particular paper. More importantly, it's not just so all of these tidal disruption events that we talk about are very rare and haven't been seen a lot in astro. So there have been roughly 20 such events known so far after like observation of say 30-40 years or so. And this particular one is even rare among them because it just shows a few of these feature lines of iron, magnesium, and calcium in this spectrum, but more or less the spectrum that we are able to see is featureless. So that is very rare for the TDEs. If you compare it with all the population that we have seen for the TDEs, most of these are featureless, but most of these shows features, including various absorption lines that we have seen in the spectrum. But this particular candidate did not show anything. There are other two candidates that we have seen so far which have shown a similar sort of spectrum. This candidate sets apart from them as well in terms of that there is an optical emission coming out of it. It's with X-ray, radio, and optical. So all the other TDEs that were featureless has none of them actually showed any sort of optical emission, and this particular candidate show you this GRP emission as well as the optical emission, which has been seen for the first time for any such class of the TDE. To summarize everything, I would emphasize that there have been 2-3 things that this paper mainly emphasizes about. One is that the discovery of these sort of transients which are rapidly evolving is something that is being transitioned into the next phase, where we require these automated boards and those can catch this very, very rapid evolution. Otherwise, we haven't been able to do that because there were none of these boards are available before this particular board that were able to keep track of all of this. You have to be really, really lucky in terms of getting something out of such sort of the GIT, which is owned by IIT Bombay itself, in collaboration with the III at Bangalore, that has played a very, very crucial role in triggering that follow campaign, which shows that there is actually a transition phase and there is a new phase coming from the TDE component, which is getting over here. Otherwise, we would have like thought it could be something like a GRP afterglow, and it would decay down the line, and we won't be able to get it. Also, this is like very, very luminous. I was not able to show the X-ray lightcurve because I was missing from the slot somehow. Those X-ray and the radio waves, it is also very, very luminous in the X-ray and radio. It's probably the most luminous object that has been ever seen in the X-ray and radio. Also, this again belongs to this very, very rare class, which is like getting evolved now, called jetted TDE, where the TDE also is launching like that. And the rate of, so we have tried to estimate the rate of the jetted TDE, which is about this 0.02 per gigaparsec cube per year, which again shows you clearly that how rare these candidates are. And with the help of these sort of boards, we will probably be able to see more of such events. But again, the intrinsic rate of these sort of events actually is low, so it will be very, very hard to get more and more such candidates until we have a very, very deep class of survey mode telescope, something like LSST, that will come in a few years. And this paper has been published a couple of months back into the Nature, and you can find more detail into this particular using this particular link. At this point, I would like to thank for your time and attention at the 5:30 p.m. on Sunday, and I would like to thank the organizers to give me an opportunity to present my work.
Thanks, sir. We have time for 2 quick questions. Why was R band chosen for the study of this jetted TD, and while the observation of over 10 days, in what frequency did you take the data acquisition through GIT?
So, GIT actually works only on the optical band, so it roughly lies from 300 nanometer to 900 nanometer or so. We tried to acquire it in only the R band with GIT. I think there are couple of points in the G and R band as well, but mainly we concentrated on R band because you have to go deeper and deeper. So if you see the magnitude time scale over here of GIT, it's, let me show this page. Yeah. So if you are able to see the magnitude around this page, it's well below 21 or so, 21 and a half or so, right? To get to reach up to this particular depth with a GIT class of telescope, you need at least a couple of hours of observation, which is, so if you want to get more and more observation in other band, you have to suppress other targets in your list, which usually doesn't happen in the thing. And we just follow the R band thing.
And when this observation was taken in Hanle, what was the duty cycle? Did we have 12 hours of data, or how many hours did we take?
So typically, we have 8 hours in a night, and this particular candidate was visible for 3 or 4 hours. So we just have 4-hour window in which we could have better reason. We are getting about an hour per night.
Okay.
From the central linear, something like a black hole is emitting cells of different energy and different particles. When they collide with each other, they form something called as forward shock, and that somewhat have been seen decaying like a power law or something like that, with an index of roughly 1.2 or so. This one actually outclassed that. It was decaying with an index of roughly 2 or so, or making it different from the GRP, typical GRP. Yes. हाँ.
I just want to know, so what is it that actually confirmed that it is jetted TD? So because,
So there was no gamma ray detected in this particular case because none of the telescope. There are few which were occulted. We don't even have like a real window around which this would have actually started because it was discovered by a optical survey instead of like a typical high energy satellite. So this rapidly rising and decaying part is what is similar to what we have seen in the detected images. Also, this pixel spectrum that we are seeing is typical for like a relativistic outflow that is coming out of your central region. So that's what confirmed that there is a jet coming out of it, plus there is this like 3D component which is coming later. Also, there was one such candidate which was in 2011 or something like that, about a decade ago, which has this opposite scenario where you don't have optical images but jetted images. So all of these property of jet part of it actually match very well with that particular. So which again confirm that it is the starting part is actually a jetted component and then there is a 3D component.
and from the observation, what can you learn about the source?
So using all of these things, we have like estimated this property of this central engine. I will read this quickly. Okay, so again the list is missing. So we have estimated the spin of the black hole, the accretion disk formation history of this particular thing, the mass that has been spent into the accretion disk and all of this by modeling this particular. There's a detailed paper coming like in a few months. This is just a discovery paper where we don't want to delay this paper because like there's a lot of work to be done, but there will be this paper shortly. Thanks, Ash, for the nice talk. The last talk